Hey all, this is, I'm just about to start a problem. So I've got a binary tree, just like this one. Find the largest subtree that's a binary search tree, where largest subtree means largest number of nodes in it. The subtree must include all of its descendants. Interesting. Let me just give the brute force. It seems like they want me to do it in O of n time. But, yeah, let's, okay, well, O of n time, I think that would just be a, I would say, an in-order traversal. And, yeah, so the idea I have is do an in-order traversal, and then pay attention to when you have nodes that appear to be sorted, but that is probably insufficient because the structure of the tree matters too. You can sort of imagine an in-order traversal that doesn't obey the binary search tree property. So maybe not that. Let me just think through the brute force. So brute force would be you've got a helper function that determines if something is a binary search tree. Basically, given this node, everything in the left subtree is smaller than this node. Everything in the right subtree is bigger than this node. And these nodes themselves are binary search trees. So yeah, okay, so that would be, the brute force would be to take that algorithm that I just said and apply it to every node. And basically you could also compute the size of the tree at each node at the same time using depth first search. So that would be quite expensive, I think, because there's a lot of duplicate work that's being done here. If you're doing, for example, if you're running the algorithm on this node and then this node, then you're visiting these nodes multiple times. So yeah, I think yeah, probably here's what we'll do. We'll simultaneously compute subtree size, and for each node we'll also just return whether or not it's, well, we'll use depth first search, depth first traversal rather. So this will return so this is a binary search tree, this is a binary search tree, so this is a binary search tree if this is also a binary search tree, this is also a binary search tree, and they obey the binary search tree property. So it seems like from each node I'm going to need to return three things. I'm going to need to return the size, also the max and min, and also the min. Interesting, this is a very hybrid problem. So this is depth first search, which is O of n, and it's the number of nodes. And space is going to be constant. I mean, not constant, but O of n, because the tree could be a linked list, or O of log n for balanced trees. Cool. So let me just start by doing a DFS. I'll just do that here. Def visit. This takes in a node and does a DFS, so finish this later. This if not node, just return I won't invoke this on something that's none. Let's assume that. So let's handle the leaf nodes, but also the normal case as well. I'll start by handling the leaf node. So if node left this way, that, then we're going to return this. We're going to return the size, which is 1, and the max and min, which are these. So that's the leaf node. Done. Check. So when it was not a leaf node, well, I would visit the left, also visit the right. As I said, I'm not going to visit them if I'm not going to visit a non-existent child. This. Let's start off with, oh yeah, and I think I would also return whether or not it's a binary search tree. So this would be size, min, max is BST. That's a crazy tuple right there. So so this is going to be size. I'll just call it left subtree size. Left min, left max. Is BST like this. I'll just shorten this to left size. That. Going to have the total size. I'll start this off as 1. I'll assume that BST is true initially. If it's disproven, then this. So the overall min is going to start off as these, and at the end I'll return size, size, and also overall min, overall max, and also is BST. Let me make this nested function actually, because I'm going to want to use a slick trick, I think. Check this out. This goes in. So max size is equal to 0. Non-local max size, so we can reassign to max size, and that's what we're going to return. That. Am I streaming? I am streaming. Okay, just making sure. It's been almost 9 minutes. Okay, so that's good. I got this right here. Same thing here, but for the right side. I'm even lazier now, so I'm just going to use R for these. Just abbreviate these to make them. I'll even do this. So let's do this. Well, if not all BST, then is BST is for false. At which point it doesn't really matter anymore. Same here. If not, otherwise you increment size. That, same here. And you're also going to update the overall min. This, as well as the overall max. That. Very simple, same here. Except R instead of max. So if it's a BST, then you want to I'm missing some logic, but I'll go back to it. But let me just skip ahead. So if it's a BST, then we'll update this size, possibly. So basically, we have to first we have to check to see that this is less than the current node. If L max is greater than node.val, this BST is going to false. Same here. If R min is less than node.val, this BST is going to false. So those are the that's a binary search tree property. The node at the root of the subtree has to be greater than everything in the left subtree and less than everything in the right subtree. I don't think there's duplicates, but we'll see. I'll do a test to see if the test cases contain duplicates, but this seems to be correct. Let me just run this. Okay. This was never updated, I suppose. So this, let me just look through this code. It's a leaf. Then we do that. We start off assuming it's true. Increment the size accordingly. This. Update these accordingly. Max like that. These are returned properly. Oh, I never called visit, that's why. Visit. Duh. Huge mistake. So if not root, return 0. See that? Has their attribute visit? What? It's right there. Let's see. Oh, I forgot to change it back to, this is a refactoring problem. Okay, that works. Let's try to add a dupe. Let's make this a dupe. So going to complain. That's fine. I think dupes are handled properly. This certainly again. Let me try something like this. The output should be 1. Oh, that's strange. Why is it 0? So root. It's a leaf. Oh, I forgot. Ah, yeah, I see. Max size is max. It's a good thing I did this. Duh. Should return 0. That's great. Yeah, I'm pretty confident in this. Let's submit it. Shit. I should have been confident. Through this tree. So I'm returning 8. 1, 2, 3, 4, 5, 6, 7, 8. So it thinks that the whole thing is a binary search tree. I'm actually inclined to agree. There are duplicates here, but in my understanding, should be fine. 2, 3, 2, 2, 2, 3, 4, 4, 5, 7. Why is the answer 2? It should be, I think it should be 8. That's what's the current time. I've spent 15 minutes so far. Okay, why? Let me see if I'm misunderstanding something. Reread the description. A subtree must include all of its descendants. Okay. This is indeed larger than everything here. This is larger or equal to everything here. Yeah, maybe maybe it wants duplicates to be on the right side. It's sort of arbitrary, but I'll try that. Okay. Let me just fix that. I'll assume that if there's a duplicate, it should go on the right side. But I think there could also be binary search trees in which the opposite's also true. So let's say if no.left, if max is larger than or equal to, okay, should do it. Alright, that's bullshit, but whatever. Solved it in 17 minutes, start to finish. It's a little bit slow, but I'll take it for tonight. It's just some decent drunken coding, I suppose. Alright, well, cheers.